So I said incorrectly in the lecture that you'll be looking at the basically lab 6 this week, but you won't because he couldn't be lab 6 in a normal year because you'd have your assessment and you wouldn't be finished with the section for the boundary value problems until, for some people, after their lab, which isn't good. So this is usually a kind of a relaxed lab. It's actually quite difficult doing the runga, but it's a relaxed lab. I don't know whether or not, I'm not 100% sure what the final VB, the final two assessments are looking like, so I can't say how important this lab is. You should. The other thing is, I think it's kind of clear that a lot of people are looking at the videos first, because there's people who are submitting. I think people are following the videos far too much. And look, I'm just going to, I mean, ideally I wouldn't actually do these videos, but unfortunately, my understanding from Bob is like it's very difficult for you when you get stuck, and it's no good you kind of emailing me. I know we can do the lab. We could have tried doing live labs, but I just thought that was going to be a complete disaster. I had no faith whatsoever. So that's why I did the videos. But if I do that, this is for just in case. Like really, if this is the first thing you've looked at, I can't see how well you're going to learn. You should be trying to do it yourself first and then consult the video. And I've said that repeatedly. Well, I said it at the start, but I'll say it again now. It is important. There's people submitting very good work weekly, but too good. They've kind of just copied me in the videos. That's not good. Okay, but anyway, let's go. So let's see. Okay, so we're doing runga. Okay, this is more state of the art. It's actually, once you've got it set up, it's very, very easy, but well, we'll see. So all of these programs are going to need a function. Now, some of them we won't have to have, there won't have to be functions of x and y, just one of them. Okay, labels, double variables, a number of double variables k, prompts for the step size go on a panel, a loop, and so a counter. Yeah, in all cases, the loop will begin by printing the current x and y. Okay, it's possible to include parameters, but we're going to keep things straightforward. Okay, so we're going to set this up. So the first one is Euler's method, but using runga. Okay, so I'm going to do, let's do a little few things. So I'll do a step size here, h, and look what we have here is temperature and time. And we'll start this off at 0.1. Okay, so the same thing is going to be, there as before. I think we'll start it with a button. Okay, and we get in like that. So option explicit as usual. So we're going to have, okay, so we'll set up the usual thing. So it's define variables, initial values, a loop which does print current, and calculate next. Okay, so the variables here, so we're going to have dim x, but x here is time, dblt, I'm going to go with time, dbl time as double, and dim dbl temp as double. Okay, we're going to have a step size, dim dbl h as double, and we probably should have, do we need a final time? No, there's no final time, we're just going up to 10, so we will need a counter though. So dim int row as integer. Oh, and then the k's. Now for Euler's method, so k isn't all these slopes. So here's just one dbl k as double. Okay, now I'm nearly going to copy this. Well, we will in a minute. So, I'll copy and paste as I go, right? So initial values, dbl time is always 0, dbl temp let's see, what's the initial value of the temperature? 90. dBLH is equal to cells row 2, column 4, I think. Row 2, column 4, yeah. Now dBLK doesn't have an initial value. Int row does. Int row equal to 2. Okay, so printing. So cells, well, that's easy. Calculate the next. So how you do this is you do it, you just literally pretty much write this. Oh, we need a function. Sorry, forgot about the big bit. Function, yeah. So we'll do the function up here, and I mean, I can't remember it either. How does it go? Here we go. Let's copy and paste, handy. So here the x is time, and the y is temp, and so we're going to have a function of time and temp. Now, if your this big F is your derivative, if your big derivative does not depend on x or y, you don't have to include that bit. So if you look at the derivative here, it doesn't actually depend on time, it only depends on temperature. So I can actually take time out, and it's just a function of temperature. And what is the function? Well, the derivative is minus 0.25 times temperature minus 20. Okay, and now we basically just write this down. So you calculate the k value, dBLK. Now I should probably call this K1. dBLK1 equal to F. Now we don't need x and y, we just have y. So dBL temp. Then you write down the next bit, but it's for, yeah, so it's for temp, dBL temp equal to dBL temp. Where am I getting this? Next y, previous y plus k, or yeah, it's dBL K1 times dBL H. And then I think after that we'll do up to time. Plus the step size. And then you're going to be looping until the time. Now you shouldn't say equal to 10. That's not what you want, because time is a real number. So until time is bigger than 10, something like that. Now, well, obviously we're not going to run that because this is just a start, but something like that. That's the basic idea, and it's going to be the basic idea all through. So let's set us up on the second one. So the second one is, this actually is Heun's measure. It doesn't look like it, but it is. So what have we got? We've got TV step size. Okay, so it's going to be pretty similar. So it's so similar, and I am going to copy and paste this much. Now what changes? What changes? First of all, the derivative. Here the derivative, so here the y and x are v and t, and also the derivative here does not depend on time, so I don't need that. So I'll change this to dBLV. And what is the derivative? It's 9.81 minus 0.0025 times dBLV squared. Okay, so I don't have temp, I have V. And now because it's Heun's method, it uses two slopes. It's dBL K1 and K2. Anything I have to change? dBL V is also equal to 0. dBL H is in the same place. Everything else is the same. So now I basically just write these formulas again. Now again, this one does not depend on time, which is the x, so I don't have to include the first bits. So I have dBL1 is, now it's not temp, it's V. dBL K2 is equal to, so you're just putting in the y bit. So it's F dBL V plus dBL K1 times dBL H. And then dBL V is equal to, use this formula, so this will be dBL V. And what is the slopes? Half the first slope, half the second slope, which is exactly Heun's method. So I can do 0.5 times K1 plus 0.5 times dBl K2. And we're going to time up equal to 30. So very, very similar, except you've got 2Ks. Now what about RK3? Okay. Rename. RK3. So this one is abstract, it's just with X and Y's. And we've H as well, putting in 0.1. So this time, let's see where we're going. I'm going to be lazy again and copy a good bit of code. So copy all this. And the name's going to be okay. Just one thing to check here. So properties. Yeah, the name of the button is okay. So this one now does depend on X and Y. So it's not just dBl-V, f of dBl-V, it's dBl-X and dBl-Y. Depends on two of them. And so the notation is X as an input is a double, Y as an input is a double, and this has to be changed. Okay. Better just put it in there. 1 plus 4 times dBl-X times square root of dBl-Y. Okay. So, so we don't have time and V here. We have X and Y. And we have a third slope. So there's 3 Ks. Initial X is 0. Initial Y is 1. H is from the same place. Intro is the same. And then, well, now you have to come down here now. And you're going to write, it's actually easier. Let me just maybe scratch most. Well, I'll put in the... Yeah, I'll do the first one. So it's actually easier because it depends on X and Y. Now the other ones, if you actually do it with X and Y, it's okay. It's just a waste of typing. The next one, so this is the X is dBl-X plus dBl-H over 2. And then look at the other one, dBl-Y plus a half times dBl-K1 times H. Okay. And then similarly do dBl-K3 and then do similarly dBl-Y. Basically write this out, and this is going until X is bigger than 1. Okay. And then the last one, which is a bit more interesting, because this one is abstract, it's not very interesting. I'm going to cut a 4. So again, now this one is, I think, V and M. It's the velocity of a rocket as a function of, so M is like the X, and V is like the Y, and we still have a step size there. Okay, again, I'm going to copy stuff. Insert button. Rob again. Okay, now there's a bit of confusion here. Okay, so what have we got here? So this time the function only depends on M. Now the M here is actually the X. So in terms of these formulas, see all these Y's, you don't need them. You can put them in if you want, but it's just a waste. So the function actually just depends on X, or in this case M, and it's minus 5 over M. Our variables are, so it's M is the X, V is the Y, so M, V, H, K1. You're also going to have K3, K4, excuse me. Initial values, M looks like 500,000, and V looks like 1,000. The rest is okay. So here you don't need the sorry, you don't need the Y's. So the first one is function of x, and the x is m. Second one, I'm just going to delete this one out, dblk2, but you don't have to put in the y's, just the x's. Also need dblk4, and keep, oh, there's no time here. So here, what's the step size? So the step size has to be mass, because that's the x, and it's saying use minus 5,000. So actually, we'll put that in here, minus 5,000. Here there's a note. It mightn't work very well. You might have to play with it a bit. So dblm plus this, and keep going until the mass is smaller than 10,000. Okay, and then plot it. Can you make any sense of it? Well, that will be in the next video. So hopefully you get an idea of what's going on there.